There are different types of neural networks. The two most popular neural networks are recurrent neural networks and convolutional neural networks. But this session is all about CNNs. CNNs designate a subcategory of neural networks. They therefore have all the characteristics of an artificial neural network. It is composed of two blocks. The first block is called convolutional base. It functions as a feature extractor. The first layer filters the image with several convolutional kernels and returns feature maps, which are then normalized and resized. This process can be repeated several times. We filter the feature maps obtained with the new kernels, which gives us new feature maps to normalize and resize, and that we can filter again, and so on. Finally, the values of the last feature maps are concatenated into a vector. This vector defines the output of the first block and the input of the second. The second block is called classifier. It's not a characteristic of CNN. It is at the end of all neural networks used for classification. The values of the input vector are transformed with several linear combinations and activation functions to return a new vector as output. This last vector contains as many elements as the classes we have. There are four types of layers for a convolutional neural network: the convolutional layer, the pooling layer, the ReLU correction layer, and the fully connected layer. I will explain how these different layers work. The convolutional layer is the principal layer, is the main layer, and this is how it functions. It drags the window representing the feature on the image and calculates the convolution product between the filter and each portion of the scanned image. The pooling layer is often placed between two convolutional layers. It receives several feature maps as input and applies the pooling operation to each of them. The pooling operation consists in reducing the size of the image while preserving their important characteristics. The most used one in practice is the max pooling. In this layer, the downsampled images are normalized by the application of the ReLU activation function. This function forces neurons to return positive values. The output of the ReLU layer is flattened and fed to the classifier, which on its turn returns a vector of size n, where n is the number of classes in our image classification problem. So here's a basic CNN architecture. But training a neural network from scratch can take anywhere from minutes to months, depending on the data and the target task. But due to computational constraints, this was possible only for research institutes and tech organizations. But with pre-trained models, that scenario has changed. Using transfer learning, we can now build deep learning applications that solve vision-related tasks much quicker. But what's a pre-trained model? Pre-trained models are models that have been already trained on some sort of data with different number of classes. A pre-trained model may not be 100% accurate in any application, but it saves huge efforts required to reinvent the wheel. There are plenty of pre-trained models used for classification already trained on some larger benchmark datasets, like ResNet, DenseNet, and VGG. But today, let's focus on VGG16 since it has the easiest architecture